This is Alcyoneus. Located 3 billion light-years away and stretching 16.3 million light-years across, it is the largest galactic structure humanity has ever discovered. The scale is so immense that even traveling at the speed of light, it would take more than 16 million years to cross from one end to the other. You could line up our own galaxy, the Milky Way, end to end 125 times and still not match the span of Alcyoneus. Light itself needs longer to traverse this structure than the entire span of recorded human history. So how does an apparently ordinary galaxy grow into a 5 megaparsec giant? In this video, we examine the secrets of the largest known galactic structure in the universe. If we truly want to understand Alcyoneus, we must place it among other cosmic giants rather than describe it in isolation. In the universe, large is a relative term. The Milky Way appears colossal to us, yet the elliptical galaxies at the centers of galaxy clusters can exceed it several times over. The real question is where Alcyoneus stands on this scale. Let us begin with spiral galaxies. The Milky Way, roughly 130,000 light-years wide and containing nearly 400 billion stars, is an enormous system. Considering that 1 light-year equals about 9.5 trillion kilometers, even light would need 130,000 years to travel from one edge of our galaxy to the other. Our nearest large neighbor, the Andromeda Galaxy, exceeds 220,000 light-years in diameter. Even that difference alone is enough to challenge the imagination. Yet when we move to the cores of galaxy clusters, the scale changes dramatically. Giant elliptical galaxies at cluster centers grow over billions of years by accreting smaller galaxies and concentrating gas toward their cores. The result can be structures several times larger than typical spiral galaxies. A classic example is Messier 87 at the center of the Virgo cluster. Much larger than the Milky Way, it is famous for the relativistic jets launched by its central supermassive black hole. These jets extend for hundreds of thousands of light-years, demonstrating that galaxies are far more than mere collections of stars. Even more extreme cases exist. At the heart of the Able 2029 lies IC 1101, long considered the largest known galaxy by stellar distribution. Its stars extend across millions of light-years, several times the size of an ordinary galaxy. Such systems are typically found at cluster centers. What makes Alcyoneus truly remarkable, however, is not just its physical size but the surprising ordinariness of the engine sustaining it. Structures of this scale are usually associated with the most massive galaxies and the most aggressive black holes. Yet data from the Sloan Digital Sky Survey overturned that expectation. The host galaxy of Alcyoneus contains only about 240 billion solar masses in stars, comparable to the Milky Way. Even more striking, the supermassive black hole responsible for launching its 16 million light-year plasma arms has a mass of only about 400 million suns. By comparison, the black hole in Messier 87 is roughly 15 times more massive, yet its radio structure appears modest beside Alcyoneus. Before Alcyoneus was discovered, IC 1101 was widely regarded as the largest galaxy known. Spanning roughly 6 million light-years and containing trillions of stars, it resembles a vast sea of light. Alcyoneus, however, extends approximately 230% farther in total structure. The crucial distinction is this: IC 1101's size is defined by its stars, whereas Alcyoneus dominates space through its radio lobes. To understand these lobes, we must examine the energy source that creates them, the active galactic nucleus at the galaxy's core. When a supermassive black hole begins accreting surrounding gas and dust, the material does not fall in directly. Due to angular momentum, it forms an immense, superheated, luminous structure known as an accretion disk. As matter spirals inward, friction and gravitational energy raise its temperature to millions of degrees. In the final moments before crossing the event horizon, powerful magnetic fields in the inner disk capture a small fraction, around 1%, of this matter and channel it along the rotational axis of the black hole. The result is one of the most energetic phenomena in the universe: relativistic jets. These jets propel ionized plasma into intergalactic space at more than 90% of the speed of light. What astonished scientists in the case of Alcyoneus is the efficiency of this process. Structures of comparable size typically require black holes with masses in the billions of suns. Yet Alcyoneus operates with what would be considered a relatively modest black hole. This suggests either exceptional efficiency in converting mass to energy or unusually low energy losses as the jets propagate through space. As the jets travel outward, they interact with the intergalactic medium, which, though extremely sparse, is not empty. Collisions with this tenuous gas cause the jets to lose energy, expand, and eventually inflate into enormous lobes that shine brightly in radio wavelengths through synchrotron radiation. Electrons spiraling within magnetic fields emit radio waves, revealing the full extent of the structure. This is what defines a radio galaxy. In visible light, the system appears relatively ordinary. In radio wavelengths, it displays two colossal wings stretching across millions of light-years. Alcyoneus exceeds not only the 1 megaparsec threshold that defines giant radio galaxies but reaches nearly 5 megaparsecs, an extreme even within that rare class. This naturally raises a fundamental question: what determines such scale? Black hole mass? Jet power? Total galactic mass? Or the surrounding cosmic environment? Evidence increasingly points to environment. The universe is not a random scattering of galaxies but a vast cosmic web of filaments and voids. Alcyoneus likely resides at the edge of a filament, expanding into a region of exceptionally low density. In such an environment, jets encounter minimal resistance, lose less energy, and remain collimated over far greater distances. In effect, Alcyoneus functions as a colossal cosmic mixer. Its jets transport heat and heavy elements across millions of light-years, influencing not only nearby galaxies but also the thermal and chemical history of the intergalactic medium. Pressure analyses indicate that the lobes remain overpressured relative to their surroundings, meaning the structure continues to expand. However, this growth is not infinite. Eventually, the lobes will encounter denser regions of the cosmic web, increasing external pressure and slowing their expansion until equilibrium is reached. Technically, it is incomplete to describe Alcyoneus simply as the largest galaxy. In terms of stellar mass, systems like IC 1101 may exceed it. But in terms of the physical distance over which a galactic nucleus projects energy into space, Alcyoneus ranks among the largest structures ever measured. Our ability to observe such giants is owed to radio astronomy. The discovery relied heavily on the Low-Frequency Array, LOFAR, a network of more than 20,000 antennas spread across 52 locations in Europe. By linking these antennas through fiber optics, LOFAR functions as a continent-sized virtual telescope. This capability revealed radio lobes spanning an angular size comparable to that of the Moon in the sky, yet completely invisible to the naked eye. In the future, more sensitive arrays such as the Square Kilometre Array may uncover even larger and fainter giants, perhaps stretching 20 or 30 million light-years. But Alcyoneus will remain a milestone, the first truly monumental example to push the boundaries of galactic evolution. From our small world within the Milky Way, when we look toward these immense radio fossils, we are reminded that the universe still holds vast mysteries waiting to be understood. For more content on astronomy and space exploration, please subscribe to the channel and express your support by liking this video.